So before starting the meeting, let me say, okay, the meeting will be recorded, but only the video of Robert Young and the speaker and its slides will be recorded. Okay, so so don't worry, you will not be, your face will not be present in the video. Okay. Also, at the end, we will ask questions and we will not record the questions. So if you're really shy, you don't want to ask a question during the talk, wait the end. Okay. But of course, we encourage to stop the speaker, Robert this time, or any other speaker next, stop and have discussions. So Robert will only speak for 45 minutes and then really leave a lot of time to discussions. And so this should be a meeting more than just a TV show, okay? Any other, for the same reason, we encourage us to leave the video on. So you can, so you can see that we are present. It's a social activity here, okay? And I think that's it. This is about the, so we start again. Unfortunately, we have a second lockdown, but let's hope to enjoy the most. Okay, so let's start. So the speaker today is Robert Young from New York University. He's going to talk about metric differentiation and embeddings of the Heisenberg group. Please, Robert, go ahead.
Thanks. So yeah, so today I want to talk about metric differentiation and embeddings of the Heisenberg group. Really, my goal is to try to convince you of two things. One, that the Heisenberg group is a three-dimensional nilpotent Lie group. It's the simplest non-abelian nilpotent group. And that non-commutativity affects its geometry. It turns out that embeddings of the Heisenberg group into Banach spaces have to be bumpy because of that non-commutativity. That's one thing I want to convince you of. And then the other thing is that, well, different Banach spaces allow bumpier embeddings than other Banach spaces. And so the Heisenberg group is going to embed better into Banach spaces that allow for bumpier embeddings. And this is all very vague. I'll try to make this a little bit more rigorous as we go on. But yeah, this is what I want to try to convince you of today. And so let me start just by quickly recalling the geometry of the Heisenberg group. The Heisenberg group is a three-dimensional nilpotent Lie group. We're going to write it as the group of 3x3 matrices with ones along the diagonal, x, y, and z above the diagonal, where x, y, and z are real numbers, but it contains a lattice, which is the set of matrices with integer coefficients, where x, y, and z are integers. And you can write that lattice as having three generators, x, y, and z, corresponding to the matrices where the x-coordinate is 1, the y-coordinate is 1, or the z-coordinate is 1, and all the rest are 0. And those satisfy some relations. The commutator of x and y is z, and x commutes with z, and y commutes with z. So this is the algebraic definition of the Heisenberg group. We are going to be interested in the geometry of the Heisenberg group, so we're going to want to put a metric on this group. The easiest way to construct the metric, or the nicest way to construct the metric, I find, is to look at the lattice, is to look at the Cayley graph of the lattice. So this is a three-dimensional Lie group. We'll identify it with R3 with an x-coordinate, y-coordinate, and a z-coordinate. And the Cayley graph is the graph where you have one vertex for every element of the group. So the elements of the lattice correspond to the lattice points in R3. And we connect two vertices by an edge if you can multiply one element of the group by a generator to get to the other element of the group. So if you start at any point and you multiply by x, it increases the x-coordinate by 1. If you start at any point and multiply by z, it increases the z-coordinate by 1. And if you multiply by y, then it increases the y-coordinate by 1. And it also changes the z-coordinate. The z-coordinate increases or decreases by the x-coordinate. And so you have this sort of tilting as you go from left to right. These blue edges corresponding to the generator y tilt as you go from left to right. Furthermore, you can see the relations that we mentioned on the previous slide in this picture. If you start at any point and you multiply x, z, or sorry, that's y, z, y inverse, z inverse, you get back to where you started. If you start at any point X and Z commute, because if you multiply X, Z, X inverse, Z inverse, you get back to where you started. And the commutator, X, Y, X inverse, Y inverse, is equal to Z, corresponding to the fact that when you go around a spiral like this, you go up one step in the Z direction. And those spirals are really important to the geometry. First, because they show up throughout the group. So for instance, here's a bigger spiral. Here's x squared, y squared, x to the minus 2, y to the minus 2, corresponding to z to the fourth, 4 steps in the z direction. Here's a larger spiral, x to the fourth, y to the fourth, x to the minus 4, y to the minus 4 is equal to z to the 16th, 16 steps in the z direction. And those spirals, one, they illustrate that the Heisenberg group has a sort of scaling. This spiral, if you stretch the x coordinate by 2, the y coordinate by 2, and the z coordinate by 4, you get this spiral. If you do that again, if you scale by 2, and then by 4, you get this bigger spiral. And in general, if you multiply the x coordinate by n, the y coordinate by n, and the z coordinate by n squared, you get an automorphism of the group that roughly scales symmetric. The other way that the spirals affect the geometry is that the spirals tend to be the most efficient ways to move vertically. This spiral like this has length 4n, it's x to the n, y to the n, x to the minus n, y to the minus n, and it's equal to the power z to the n squared. It moves n squared steps in the z direction. And when n is large, that spiral is going to be a lot shorter than the corresponding path, the corresponding vertical path. And so in particular, if you take 2 points in the Heisenberg group that are very far apart, say a point over here and a point over here, and you look at the shortest path in the graph between them, that shortest path can't contain too many black edges, can't contain too many vertical edges. Because if that path contains a lot of vertical edges, then you could get a shorter path by replacing that with a spiral. So the number of vertical edges in a shortest path is bounded. And that's a big effect on the geometry. So this is the this is a picture of the lattice. This defines a metric on the lattice. But what we really want is we want a metric on the Lie group. So we can turn this into a metric on the Lie group by taking a scaling limit. So remember, we went from here to here by shrinking the x coordinate by 2, the y coordinate by 2, and the z coordinate by 4. If we keep on going like that, if we scale x by n, y by n, z by n squared, we'll get a sequence of denser and denser graphs in R3, and we can talk about the limit of the metric on those graphs. That limit, because of the n by n squared scaling, that limit metric should also have an n by n squared scaling, and because shortest paths in the graph only have finitely many vertical edges, shortest paths in the limit should really have no vertical edges, because as you do this scaling, those vertical edges get smaller and smaller. If there are only finitely many vertical edges, then in the limit, those finitely many vertical edges should just collapse to nothing. So shortest paths in the limit should be made up essentially entirely of red and blue edges. And when you have that, that's a Sub-Riemannian metric. That's a metric that's determined by some collection of horizontal planes. In this case, these are the planes that are spanned by the red and blue edges, so they tilt as you go from left to right. Curves that are tangent to these planes are called horizontal curves. We define a distance function on this, we define a corresponding distance function where the distance between 2 points is the length of the shortest horizontal curve between those 2 points. And that picks up a lot of the properties we had from before. So for instance, the scaling from before carries over. If you multiply x by t, y by t, z by t squared, it scales the metric by a factor of t. That has a strong effect on the geometry because it tells you that the ball of radius epsilon around 0 is the scaling of the ball of radius 1 around 0. The ball of radius 1 is roughly a 1 by 1 by 1 cube. So the ball of radius epsilon is roughly an epsilon by epsilon by epsilon squared box. And that means that every one of these vertical lines has Hausdorff dimension 2. If I want to cover this segment by balls of radius epsilon, I need epsilon to the minus 2 balls in order to do that. So each of these vertical lines has Hausdorff dimension 2. And what that means is that this picture is not really very geometrically accurate. Because all these vertical lines have Hausdorff dimension 2 in the Heisenberg group, but we're drawing them as lines. We're drawing them as one-dimensional objects. We aren't seeing the real geometry of the Heisenberg group. So a natural question to ask is, well, can we see the real geometry of the Heisenberg group? Can we embed the Heisenberg group in Euclidean space in a way that preserves the metric? And the answer is no. There's a theorem of Pansu and Semmes that there's no bilipschitz embedding from the Heisenberg group or from the integer lattice in the Heisenberg group to Euclidean space. So remember, this talk is about metric embeddings of the Heisenberg group. This tells us that there are no metric embeddings of the Heisenberg group or of the lattice in Rn. So what do we do next? Well, we can't embed the whole Heisenberg group in Rn, but we can embed pieces of it. We can embed pieces of the Heisenberg group in Rn. And so we can ask, okay, any finite piece of the Heisenberg group, any finite piece of the lattice embeds in Rn because, well, as long as you send every point to, as long as you construct an injective map, it's automatically bilipschitz. An injective map from a finite metric space is automatically bilipschitz. But how does the difficulty of embedding pieces of the Heisenberg group into Rn grow as the pieces get bigger and bigger? What are the asymptotics of embeddings like this? So to make this more rigorous, let me define the notion of the distortion of a bilipschitz embedding. If M is a metric space, X is a Banach space, F is a bilipschitz embedding with distortion D. If it's a distance decreasing map, if the distance between f of p and f of p1 and f of p2 is less than or equal to the distance between p1 and p2, so it's a distance decreasing map, but it doesn't decrease distances by too much. It decreases distances by at most a factor of d. In that case, we call it a bilipschitz embedding with distortion d, and we define the X distortion of M as the infimo distortion for which such a map exists. Is this okay so far? Okay, so then we can state the following theorem of Assaf Naor and tessera. If BR is the ball of radius R in the integer Heisenberg group, so this is a metric space with roughly R to the 4th elements, then the L2 distortion of V sub R is on the order of the square root of the log of R. So the ball of radius R embeds in Hilbert space with distortion roughly root log R. So as R increases, this distortion increases, which makes sense because we know that we can't embed the entire Heisenberg group. We can't embed the entire lattice in Hilbert space. And so it makes sense that as we try to embed larger and larger pieces of the Heisenberg group, it becomes more and more difficult. More generally, we can ask, okay, well, so this is how hard it is to embed the Heisenberg group in Hilbert space. What about other Banach spaces? What about other LP spaces? And there's a lot that's known. So if BR is the ball of radius R in the integer Heisenberg group, then you can embed it in L1 with distortion on the order of the 4th root of log. The first result in this direction was due to Chigo, Kleiner, and Naor. And then recently, Assaf and I have found sharp upper and lower bounds on this distortion to get this asymptotic estimate. And for larger P, you have a formula like this. You can embed the ball of radius R in LP with distortion like log R to the power of 1 over the max of P and 2 for any P greater than 1. And this is due to, the upper bounds are due to Assaf and tessera, the lower bounds are due to Austin, Naor, and tessera in the case P equals 2, and Laforgue and Naor for arbitrary P. So this is a lot of information to take in. So let me write it as a graph instead. If we write it as a graph, we get this, that the distortion of embeddings of the ball of radius R into LP spaces, you have this plateau. The hardest LP spaces to embed in are when P is between 1 and 2. Then it gets easier as P increases. And also it has this discontinuity here where it also gets easier in L1. And so let me try to explain a little bit about this graph. So like I said, there are three pieces here. We have this piece where it's decreasing as p gets large. It's hard when p is between 1 and 2, but it's constantly hard. It's the same level of hardness. And then we have this discontinuity at p equals 1. So decreasing as p gets large is relatively common. There's a theorem of Kuratowski that any metric space embeds isometrically in L infinity. And so as p gets larger and larger, we get our target space gets closer and closer to L infinity. And so we should expect that the embeddings get easier and easier as p gets larger and larger. So this part of the graph is relatively common. The plateau between 1 and 2, again, there's a reason for that. There's a theorem of Dvoretsky that any infinite dimensional Banach space almost contains a copy of Hilbert space. So if you want to embed in an arbitrary infinite dimensional Banach space, it can't really be harder than embedding in Hilbert space because your infinite dimensional Banach space contains almost a copy of Hilbert space. And so you can just embed in that copy of Hilbert space. So the fact that this is constant between L1 and L2, that's really explained by this Dvoretsky's theorem. The discontinuity at L1, that's very special. This is the only metric space we know of that has this discontinuity when you go from L1 plus epsilon to L1. This seems to be specific to the 3-dimensional Heisenberg group. Even if you go to the 5-dimensional Heisenberg group or the 7-dimensional Heisenberg group, this discontinuity disappears. And in fact, we can use this discontinuity to prove a neat fact about the geometry of Banach spaces, which is that there's a metric space based on the Heisenberg group that embeds bilipschitzly in L1 and L4, but not in any LP space in between. And the way you construct this is basically you take this ball of radius r, you distort it just enough to get it to fit bilipschitzly in L1. So that takes about log r to the 1/4, 4th root of log distortion. That amount of distortion is also enough to get it to embed bilipschitzly in L4, but it's not enough to get it to embed anywhere in between, because anywhere in between you need more than 4th root of log distortion to get a good embedding. So yeah, so what I want to do today is I want to try to explain this graph in a little bit more detail and try to explain one, well, I guess two main things. One, what's happening for large p, for p bigger than 1, and then two, try to explain what we've done that's new in L1 and why there's this discontinuity for L1. Okay. Okay, is this okay so far? Are there any questions about anything so far? Okay, so let's do this. So let's start by looking at embeddings of the Heisenberg group in LP spaces. Yeah.
May I ask a question?
Uh-huh.
Which LP spaces are you considering? Is it of the LP of like sequences of on the integers or sequences?
So because these are finite metric spaces, it doesn't really matter too much. But I mean, for our purposes, we'll just take LP of the LP either of the interval or LP of the real line. But it doesn't matter too much because because these are finite metric spaces. So any embedding lies in some finite dimensional subspace. Okay. Okay. So yeah. So let's start by looking at maps to LP spaces when p is bigger than 1. And in that case, we have this theorem of Pansu and Semmes that there's no bilipschitz embedding from the Heisenberg group to Rn. And in fact, this generalizes, Cheeger and Feiner generalize this to any, there's no bilipschitz embedding from the Heisenberg group to any Banach space with the Radon-Nikodym property. So any LP space where p is bigger than 1, less than infinity. But this theorem is based on a differentiability argument. It's based on a theorem of Pansu that says that any Lipschitz map F from the Heisenberg group to Rn is Pansu differentiable almost everywhere, which means that if you look at your map on sufficiently small balls, then it looks like a homomorphism, that your map is approximately a homomorphism on sufficiently small balls. But any homomorphism from the Heisenberg group to Rn has to send z to 0. And so if your map is close to a homomorphism, that means it has to collapse that z direction. This is worth looking at a little bit more closely, because our goal here is really to construct good embeddings from the Heisenberg group into Rn, construct the best embeddings we can from the Heisenberg group into Rn. So in order to do that, well, this theorem tells us that every Lipschitz map has some ball on which the z-axis collapses. In order to avoid that, it would be helpful to know why the z-axis collapses, why there's some ball where the z-axis collapses, so we can avoid that thing, so we can construct embeddings that avoid that thing as much as possible. So let's look at this a little bit more closely to try to figure out what we need to avoid when we construct embeddings later. So Pansu's theorem is roughly based on, well, is roughly based on Rademacher's theorem, or one way to prove Pansu's theorem basically uses Rademacher's theorem, and the fact that the Heisenberg group is sort of foliated by these red lines going in the x direction, and these, it doesn't really show up very well, but the lines in the y direction are supposed to be blue. So it's foliated by these red lines in the x direction and these blue lines in the y direction. And so if the Rademacher's theorem tells you that if you have a Lipschitz map, well, let me put it this way. So if you have a Lipschitz map, if you have a Lipschitz map from the Heisenberg group to Rn, then the restriction to one of these red lines is going to be a Lipschitz curve. Rademacher's theorem tells you that any Lipschitz curve is differentiable almost everywhere, which means that we can take some small, around almost every point, we can take some small ball, where if we blow up around that ball, then we get something that's close to a line. But we don't just have one red line, we actually have a foliation of red lines. And with a little bit of measure theory, we can actually do a little better. We can find a ball where all of the red lines in that ball map to nearly straight lines in Rn. And in fact, they map to nearly straight lines that are going in nearly the same direction. So all the red lines in some ball map to nearly parallel lines in Rn. And the same thing for all the blue lines in the ball. We have a bunch of blue lines in the ball. And again, we can find some small ball where all those blue lines map to nearly parallel straight lines in Rn. But then that's a problem, because remember, in the Heisenberg group, if you start at a point and you go x, y, x inverse, y inverse, you end up far away from where you started. If you go around a spiral, you end up above where you started. You end up about, if this length is r, you end up about r away from where you started. But then when you look at the image of this spiral in Rn, you're starting at a point, you're following a red line, a blue line, a red line back, a blue line back. You're tracing out a parallelogram, you end up very close to where you started. So the reason that a Lipschitz map has to collapse the z-axis, or one of the reasons why a Lipschitz map has to collapse the z-axis, is because a Lipschitz map is always going to have some ball where all the red lines and all the blue lines map to parallel lines, and inside that ball, spirals map to parallelograms, and so the z-axis collapses. Therefore, if we want to construct a map where the z-axis doesn't collapse, if we want to construct a map that preserves the geometry of the Heisenberg group, this is exactly what we need to avoid. We need to make sure that that as much as possible, when we look at balls when we look at the balls in the Heisenberg group, the red lines don't map close to lines, and the blue lines don't map close to lines. This map we have a problem because our map is approximately linear. In order to avoid that, we need to make maps that are bumpy. Okay. So how do we do that? How do we construct maps that avoid this differentiability as much as possible? Well, the standard example of a map that's not differentiable anywhere is the Weierstrass function, right? And you construct the Weierstrass function from a sum of sine waves, essentially. You have a big sine wave, and you add a smaller sine wave, and a smaller sine wave, and a smaller sine wave, and you sum them all up, and there's enough oscillation that the derivative is not defined anywhere. And you can do essentially the same thing for the Heisenberg group. You can do essentially the same thing. This is an argument due to Aswad. What we're going to do is we want to embed the ball of radius r. Let's take r to be a power of 2. So r is equal to 2 to the n. Let's construct a sequence of Lipschitz maps, one Lipschitz maps f sub I, f1 through fn, from the Heisenberg group to L2, where each of these maps is bumpy at a different scale. F sub I is bumpy at scale 2 to the I, which means that we're going to have f sub I, we're going to have the image of f sub I be contained in, say, the ball of radius rho to the I, or that's supposed to be a 2 to the I. And we're going to ask that if I have 2 points that are separated by roughly distance 2 to the I, then their images are also separated by distance roughly 2 to the I. The example to think about is just, sine waves, except instead of the example you want to think about is sort of is sine waves. So if we have a sine wave, it tends to separate points that are about separated by half an amplitude, and we can talk about sine waves of one frequency and then a smaller frequency and then a smaller frequency and so on. So these are not too hard to construct. In fact, because of the scaling of the Heisenberg group, it's enough to construct one of these maps and then take scalings of it to get all the different f sub i's. And then we construct one big map f by adding a bunch of copies of these together. We define capital F is the sum from I equals 1 to n of 1 over root n f sub I. So we rescale each of the f sub I by a factor of root n, and we stick them all in orthogonal subspaces of L2. Because we have n terms that are each 1 over root n Lipschitz, orthogonality tells us that this is 1 Lipschitz. And it turns out that this does reasonably well at separating points. This preserves the metric reasonably well. Because if I take 2 points in BR, then these are points in the integer lattice, so they can't be too close together. The distance between them is at least 1. And they're points in the ball of radius r, so the distance between them is at most r, at most 2 to the n. So that means that there's some I, so that the distance between Q1 and Q2 is close to 2 to the I. And that means there's some f sub I, so that the distance between f sub I Q1 and f sub I Q2 is at least C inverse times the distance between Q1 and Q2. And that means that the distance, so since big F contains that f sub I, albeit scaled by root n, that means that big F separates Q1 and Q2 by at least C inverse over root n times the distance between Q1 and Q2. And at most, because of the Lipschitz bound, at most the distance between Q1 and Q2. And that means that F has distortion at most C root n, which is, say, it has distortion at most root log r on the ball of radius r. So this is a map which is not linear at any scale, because these maps are each f sub I is nonlinear at scale 2 to the I. So this map is not really close to linear at any scale. And because of that, it has low distortion. Its distortion is only on the order of root log r. Is this okay? Is this construction clear? Okay. So this is all for L2. You can do the same thing in LP. The main difference in LP is that instead of having 1 over root n, you can use larger coefficients in LP than you can in L2. And so in LP, this argument gives you a distortion of log r to the power of 1 over max of p and 2. And that's optimal. There's a theorem of Laforgue and Naor, which says that the LP distortion of this ball is at least that much. So this is just about as good as well as you can do when p is bigger than 1. And so that really explains, if you remember this graph from before, that covers the part of this graph that goes from here to here. That covers the part of the graph where P is bigger than 1. So what's left is P equals 1.
Robert,
And P
one
equals,
question. Can
yeah.
I ask you a question? So what you just recall us, this is the proof of the Assaf embedding theorem.
Yes, exactly.
Correct? And this is for the snowflake or with exponent 1/2.
Well, so the Assaf embedding theorem works with snowflakes with arbitrary exponent 1 minus epsilon, but the distortion depends on it. But there are various parts of it that depend on epsilon.
Yeah. So I was wondering, is there a reason why the best one is obtained when you snowflake by 1/2?
We're not really snowflaking by 1/2. I think if you want to do this using the Assaf embedding theorem, you end up snowflaking by something like 1 minus 1 over log r, or 1 over root log r. Yeah, 1 over. You end up snowflaking by 1 minus 1 over log r. And the reason you want to snowflake like that is because you're dealing, so it's really about this. The distances you're interested in are all distances between 1 and 2 to the n, between 1 and r. And so that's log r many distances. If you snowflake by an exponent that's sufficiently close to 1, then it only changes those distances by about a constant. And so you are snowflaking, but that snowflaking is the same as a bilipschitz map.
Okay. Thanks.
Okay.
Thanks a lot. Yes. Thanks.
Yeah. So that's for P greater than 1. What happens at P equals 1? So P equals 1 is very different from P greater than 1, because when P is greater than 1, the LP has the Rademacher property. LP has a version of Rademacher's theorem. Any Lipschitz map to LP when P is bigger than 1 is differentiable almost everywhere. In L1, that's not the case. And so in LP, you couldn't have a map that's bumpy everywhere. You couldn't have a map that's far from linear at every scale, because that would violate Rademacher's theorem. In L1, you can. Lipschitz maps to L1 need not be differentiable anywhere, and in fact, you can draw. You can construct an example. F taking the interval to L1 on the interval. F of t is the characteristic function of the interval from 0 to t. You can calculate that this is an isometric embedding, but it's an isometric embedding that cannot be approximated by a Lipschitz map at any scale. No matter how far you zoom in on this map, it never gets close to linear. In the terminology we were using before, this is sort of infinitely bumpy. It's not close to a linear map at any scale, and so you can't use the arguments we used before to bound the distortion of maps like this. And in fact, you can construct maps like this that have less distortion than the maps we constructed earlier. So the way I'm going to do that is I'm going to construct maps that are kind of inspired by this example. I'm going to construct maps that are from the Heisenberg group to the set of L1 functions on the Heisenberg group that send every element of the Heisenberg group to a characteristic function, to a 0,1 function. Specifically, I'm going to look at maps that are equivariant, maps of the following form. So I pick a subset of the Heisenberg group. I let mu be the Haar measure in the Heisenberg group, and then I define a map f sub s from the Heisenberg group to the set of L1 functions, which sends each element g to the characteristic function of g s inverse. Then it's straightforward to calculate the metric that this induces. FSP minus FSQ is the difference between these two characteristic functions. The difference between these two characteristic functions is the same as the measure of the set of points in H, such that the translate GS contains one of either P or Q, but not both. So this is the measure of the set of translates of S that separates P and Q. This is a little bit, so it's worthwhile. So it's worthwhile thinking about this for a bit. So let's look at an example. Let's take let's take D to be the unit ball. in the Heisenberg group, and then let's consider f sub d. So remember what this does. This takes g to the characteristic function of g d inverse. In this case, it's symmetric. This is just the same as d. And then the distance between fd of p1 of p and fd of q is the measure of the set of translates such that gd contains p or q, but not both. So what does this do? Well, if p and q are far apart, let's say their distance is at least 2, then when we look at translates of the unit ball that contain either of these, well, if I have a translate of the unit ball that contains p, then it doesn't contain q. If I have a translate of the unit ball that contains q, then it doesn't contain p. And so this measure is just the measure of the set of unit balls that contain p plus the measure of the set of unit balls that contain q. And so if d is bigger, if the distance between p and q is large, then that means that the distance between f of p and f of q is some constant. Is some constant. If the distance between p and q is small, then it depends on the direction between p and q. Because if p and q are close together and they're separated by a horizontal line, say a horizontal line of length t, then what are the translates of the ball that contain p but not q, or q but not p? Well, there are translates that look like that, right? They're translates that intersect this horizontal line segment. Either they contain p but not q, or they contain q but not p. And there are roughly t of those. The measure of those translates is about t. The same thing happens if p and q are separated by a vertical line. If p and q are separated by a vertical line, by vertical distance t, then again, there are about t translates of the unit ball that contain one or the other, but not both. But the problem is that, well, vertical distances in the Heisenberg group are much larger than horizontal distances. So even though we kind of see the same thing for horizontal and vertical line segments, so if the distance between p and q is at least is large, then the distance between fd of p and fd of q is about a constant. If p and q are separated horizontally, then their images are separated by about the same amount. But if p and q are separated vertically by z to the t, then their images are separated by about t, but that t is much smaller than the distance between p and q, because the distance between p and q is the square root of t, which could be much larger than t itself. So this map, if we take f sub d, where d is the unit ball, then this map embeds horizontal lines pretty well. It preserves horizontal distances pretty well, but it's collapsing. It collapses the vertical lines. It sends points that are vertically separated by root t to points that are separated by distance t instead. Is this okay so far?
I'm sorry, may I ask a question?
Yeah.
May I ask a question? S here is a unit ball as H considered as a Euclidean space or as a Sub-Riemannian space?
It doesn't really matter. They're about the same.
Ah, okay, thanks.
I mean, what we'll see is that so the important thing turns out to be not really the coarse behavior. The important thing really turns out to be the texture of the surface, how rough and how rough or how smooth it is. And so I'm going to try to explain that in a bit. But like the difference between the Euclidean ball and the unit Heisenberg ball is really it doesn't really matter very much here. Okay.
Yes, yes. Now I see. Thank you very much.
Okay. So this embeds horizontal lines well, but it collapses vertical lines. How can we fix that? How can we find a set that gives us a better embedding of the vertical lines? well, in order to get a set that, in order to get a better embedding of the vertical lines, we need a, well, we kind of need a more complicated D. Say we have some D, like, you know, some more complicated set, because well, we've been, I wrote that the distance between f of p and f of q is the measure of the set of translates of the set that contain one but not the other. But you can turn that around. You can also say that the distance between f of p and f of q is the number of translates of the segment between p and q, the number of translates of the segment between p and q that cross from inside the set to outside the set. So if we have a more complicated set, there are going to be more translates that cross the boundary of that set. And so in particular, if we have a more complicated set and p and q are vertically separated, there are going to be a lot more vertical lines that cross the boundary of the set. And so the images of p and q are going to be separated more. So is that okay? The problem, though, is that, well, the horizontal lines were already separated the right amount. And if we make the set more complicated, then that's going to also increase the separation of horizontally separated points, because horizontal lines are going to intersect the boundary of the set even more if the set, if the boundary is very complicated. So really our question is this: how do we find some set that cuts as many vertical lines and as few horizontal lines as possible? How do we construct a set which is, well, I call this a bumpy surface, because, well, imagine how you construct this, or think about how you would construct something like this. Say start with a surface that's just the YZ plane here, this vertical plane off to one side, where I have these blue lines going just front to back on this vertical plane. This doesn't intersect any vertical lines, but we can make it intersect vertical lines by perturbing it. And if instead of the Heisenberg group looking like this, if instead the blue line just went straight front to back, if all the blue lines were absolutely parallel, then it would be easy to perturb this to cut extra vertical lines with the same number of horizontal lines, because we could just sort of add a hump there and a hump there. Just I've always had difficulty drawing this, but what I want you to imagine is a surface that looks like a surface like this, right? Where you sort of corrugate the surface, where the surface follows a sine wave. If you do that, then, well, if the horizontal lines were absolutely parallel, were all parallel to the y-axis, then those horizontal lines would just go straight through this bump, straight through this corrugation. We wouldn't intersect any extra horizontal lines, but we would intersect all the vertical lines that go in and out and in and out of these humps. So if both these foliations were absolutely parallel, this would be easy. They aren't, but this is still a reasonably good starting point. Even though these aren't parallel, it's still the case that if I take my vertical plane, and if I take, say, an ellipsoid that's stretched out along one of these horizontal lines, one of these blue lines, and then I add a bump function supported on that ellipsoid, then I cut a lot more vertical lines, because there are a lot of vertical lines that go through this, this bump. But I don't cut as many horizontal lines, because most of the horizontal lines, even if they do tilt up and down, they mostly go along this bump. And so I can do a first step of my construction by just adding bumps to the vertical plane that are stretched out along the horizontal lines. That does a good job of separating points that are vertically separated by about, say, that much. Because if I have a line segment about that height, then there are going to be a lot of translates of that line segment that go in one bump, that cross the boundary of one of these bumps. But it doesn't do as good a job at dealing with points that are separated by just a smaller amount. Because remember, vertical lines have Hausdorff dimension 2. So I should have, so if I take a vertical segment of, say this is length 1, say this is length 1/4, if I have some number of, if some number of translates of this that cross the boundary, I should have half the number of translates of this that cross the boundary. And if I have a nice smooth surface like this, I'm only going to have 1/4 of the translates of this that intersect the boundary as compared to the translates of this. So I need to do something additional to deal with the smaller scale, which is to say I need to add more bumps. I need to add bumps that are about this high. And that we can do. The main difficulty is that when we do this, because the horizontal lines start to tilt, our next set of bumps is going to have to be slightly tilted with respect to this set of bumps. And then that'll deal with so we'll add smaller bumps that are slightly tilted. And then on top of that, we'll add even smaller bumps that are tilted a little bit more, and so on and so forth, until after logarithmically many layers of bumps, we've added enough bumps to separate all the vertical lines of scales between 1 and the size of the ball. So, and that's and in fact, that's what we do. We construct these bumpy surfaces by starting with a vertical plane, adding just one big bump in the center. That's going to affect the shape of these horizontal lines. That's going to cause them to tilt in the middle of that bump. And so that's going to affect when we add the next set of bumps. That next set of bumps is going to start to tilt a little bit. It's going to follow those horizontal lines from the previous set of bumps. And then when we add the next set of bumps, it's going to tilt even a little bit more. As we add more and more bumps, it pushes it away from the original vertical plane. The horizontal lines start to tilt more and more. And so each next set of bumps is a little bit more tilted than the last. And so, but what we end up with is a surface like this, which is very bumpy because, well, if I take a vertical line, it's typically going to go in and out and in and out and in and out of these bumps. But if I take a horizontal line, it's typically going to go in one side of a bump and then out the other side of the bump. We haven't increased the horizontal perimeter much, but we have increased sort of the vertical perimeter. Specifically, if you wanted to quantify this, if we add a layer of bumps of depth epsilon, it adds epsilon to the fourth to the perimeter. So if we want logarithmically many layers of bumps, then they're all going to have depth on the order of log r to the 1/4 minus 1/4. And that depth is enough to, it cuts enough vertical lines to give us distortion on the order of 4th root of log. And that's essentially optimal. So yeah, so the natural question, which I don't have time to answer, is whether this is actually optimal, whether this is the bumpiest surface you can build. Turns out it is. This is up to a constant, the bumpiest surface you can build in the Heisenberg group. The reason why is another talk, I guess, but roughly you can take an arbitrary surface, you can break it down into intrinsic Lipschitz graphs. Intrinsic Lipschitz graphs are surfaces like this. You can see you've got the same sort of properties as these bump functions, in that if you go vertically, you can go in and out of all these little spikes in the graph. But if you go horizontally, you just kind of go along one of these valleys or along one of these ridges. You don't really cross the surface very much. And you can make that rigorous. You can, given an intrinsic Lipschitz graph, you can construct something called a foliated corona decomposition, which consists of quadrilaterals of varying shapes and sizes, on which the graph is nearly foliated by lines, and it satisfies a bound that that a graph with such a decomposition can't be much bumpier than the surface we constructed. And in fact, these decompositions are basically the reverse of what we constructed. It takes some arbitrary bumpy surface and it breaks it down into a bunch of roughly rectangular regions so that the foliation on each rectangular region is relatively well behaved. In the case of our bumpy surface, it more or less breaks the surface down into all the bumps that make it up. So yeah, so just to conclude, the short version of this talk is the following. Maps from the Heisenberg group to Hilbert space are governed by the differentiability and the bumpiness of curves in Hilbert space. maps from the Heisenberg group to L1 are governed by the rectifiability and the bumpiness of surfaces in the Heisenberg group. And furthermore, surfaces in the Heisenberg group, surfaces in the three-dimensional Heisenberg group are very different from surfaces in the five-dimensional Heisenberg group. This construction we just did, where we align the bumps along the horizontal lines, you can't do that in the five-dimensional Heisenberg group. In fact, any surface in the five-dimensional Heisenberg group can be epsilon bumpy at no more than epsilon to the -2 different scales, whereas in the three-dimensional Heisenberg group, you can be bumpy at epsilon to the -4 different scales. And that's the reason why the distortion of the three-dimensional Heisenberg group is fourth root of log, and the five-dimensional Heisenberg group has square root log distortion. So, okay, thanks.
Thank you, Robert. Thanks for the talk. Let's start the discussion or questions. Are there questions?